Good morning, everyone, and welcome to the second seminar of the WST time domain working group series. This series highlights the work of researchers in time domain astrophysics with short talks followed by open discussion. Each session is 20 minutes long with 10 minutes for questions and discussion at the end. It's a pleasure to introduce today's speaker, Dr. Michele Trabucchi. Michele is a researcher at the University of Padova. He earned his PhD in Padova in 2018 as a part of the ERC funded SARCAD project. His work focuses on the theoretical modeling of pulsating stars, especially long period variables, their role in stellar pulsation studies, and as distance indicators. He is part of the Gaia consortium, and he contributed to the LPV Gaia catalog, and he is now the PI of the Convergence project, which studies the impact of binary companions on pulsating mass-losing stars. He's involved in several international collaborations like Gaia for sure and Rubin LST collaborations. Please join me in welcoming Dr. Michele Trabucchi. Michele, thank you for being with us today. The floor is yours.
Thank you very much. And I'm happy to thank both Julia and Fatime for inviting me and for organizing this. You probably already saw the disclaimer in my subtitle, so take what I say with some gramo salis, the Latin to say. I asked myself, looking at the white paper, what WST can be expected to do for people like me who love long period variables. So today I will try to give you an overview of these objects and some ideas that I had playing around with the information about WST. So long period variables, basically, we're talking about cool, luminous red giants at the end of their life. So here you have few numbers. We're talking about objects, roughly speaking, hundreds to tens of thousands times brighter than the sun, but just as hot as a few thousand degrees. So as I'll mention later, this is the typical surface temperatures at which molecular chemistry and dust formation occur and play an important role in the structure and evolution of stars. And these are sizable stars. So once again, these are crude numbers, but we can expect them to be as large as almost 1,000 solar radii. And this is why, and I wanted to immediately show you this image, although I'm not going to talk about this, when nearby, we can actually image these stars by near-infrared interferometry. This is work there in Nature 2018 by Claudia Palladini. So these are really exciting objects to deal with. And of course, I'm interested in periodic variability of these stars. Once again, quite a heterogeneous behavior because we have periods ranging from a few days to years and spanning a range of photometric amplitudes to a millimagnitude level up to several visual magnitudes of change in the case of the so-called Miras. So indeed, let me introduce the typical classification of these stars from the standpoint of variability. There are actually a number of different classifications because LPVs are a various family of diverse objects, but usually we recognize Miras, semi-regular variables, and a number of flavors of small amplitude red giants. Historically, irregular variables have been adopted as a scheme of classification, but my personal opinion, as also admitted in the general catalog of variable stars, is that most, if not all, irregular variables are perhaps just poorly studied, so not intrinsically irregular, but just missing some important observations. And indeed, in this sense, the large-scale optical time domain astronomical surveys in the past 30 years played an important role. So I'm going to show often data from the optical microlens gravitational lensing experiment, who played an important role in studying these objects. So let me just give you an idea of what Miras are. These are the most spectacular among long period variables, identified by the amplitude of visual changes being above 2.5 magnitudes, usually monoperiodic, as you can see here, and therefore quite regular, with periods peaking at around 400 days, but they can be much longer. This is an extreme case of an oxygen-rich Mira and a small Magellanic Cloud with almost 2,000 days period. So this really gives you an idea of how important it is to have long time baseline observations to study these objects. And this is already a hint to what WST can be expected to do in terms of time domain. Now, I'm not going to spend a lot of time on this, but semi-regular variables instead, by the name themselves, are qualitatively identified by being less regular than Miras, although the actual classification is typically based quantitatively on their amplitude. It's a bit arbitrary, but you can get an idea of the diversity of these stars. These are examples, once again, from Ogle, Large Magellanic Cloud. When you fold the light curves by the primary period, because of course these are multi-periodic, you take the strongest periodic signal, you fold the light curves, and you see that it's a bit smeared out in this case, better definite in this case. So you have a variety. Some of these stars are much more similar to Miras than what we would expect from the name, from their classification. And then, as I mentioned, with the recent large-scale surveys, people have identified a number of, a pattern of regularity in objects that we used to think were irregular. An important class are the so-called OSERCs, which stands for Ogle, optical gravitational lensing, small amplitude red giants, term coined by Ray, Ayer, and Paczynski in 2004. They actually represent the largest fraction of long-period variables in many catalogs. These three disks are pie charts, are the three catalogs from the Ogle 3 program, the Galactic Bulge and the Magellanic Clouds. You see that the largest slice is OSERCs, while semi-regulars typically occupy 10 to 15% of the catalog, and Miras are around 2%. That's because Miras represent quite a narrow window in the evolution of these stars. So let me connect with stellar evolution. I'll actually go backwards because of the structure of this HR diagram populated by different classes of pulsators and variable stars. And looking at the giant branch where we found the decreasing the Miras, SRB, OSERCs, so they actually represent approximately an evolutionary sequence, at the end of which we have Miras that are thermally pulsing asymptotic giant branch stars. So the terminal stage in the evolution of low to intermediate mass stars. Semi-regulars typically are early or thermally pulsing AGB stars, but then again, it's an approximate identification. Some of these stars are red supergiants, which means cool core helium burning massive stars. And OSERCs are either early AGB stars or red giant branch stars. It's worth mentioning that if we go backwards again in this sequence to shorter periods, smaller amplitudes, hotter stars, lower luminosities, and earlier evolution, we encounter Xi-Hydra stars, which are solar-like oscillators on the red giant branch, and they're actually related with OSERCs, as I'll mention later. The common feature between these objects is that they all have quite extensive convective envelopes, as they are close to the Hayashi line in the evolution. Now, a key tool for studying these stars is the period luminosity diagram, of course. Now, owing to Wood and collaborators 1999, who used macho program data to study the stars, we now know that there are at least six different period luminosity relations or sequences in the diagram. Usually we employ optical variability data combined with mean near-infrared photometry to study the stars, because the peak emission happens in the near-infrared. The basic idea is that we have 6 sequences. Some of them are due to stellar pulsation or more in general oscillations, but I'll stick to radial pulsation. Some of them are due to other processes. It's a complex business, because actually just 4 pulsation modes, so 4 distinct types of acoustic stationary waves in the envelope, are responsible for 5 sequences. So the basic idea is if we start from short periods, we have this sequence that's labeled A prime is caused by dominant pulsation in the third overtone mode. We have a sequence A caused by dominant pulsation in the second overtone mode. And both these sequences that are populated respectively in green by Ozarks and in orange by semi-regulars, these are labeled B and C prime and are both caused by pulsation in the first overtone mode. Whereas the sequence C populated by Myras and semi-regulars is due to the fundamental mode of pulsation. Now, the basic idea is that stars on the giant branch evolve, becoming brighter, cooler, and larger, so they expand. And as they do so, different pulsation modes become active, excited, and dominant. This is sketched here with the same evolutionary track of a 1.5 solar mass star at LMC metallicity, shown multiple times, one for each different pulsation mode among these ones. And as the star evolves, the third overtone mode is dominant, forming a period on sequence A prime, then it shuts down, the second overtone becomes dominant on sequence A, and so on until fundamental mode pulsation. Once again, this is quite tricky. It's not trivial to model these stars because once we get to large amplitude fundamental mode pulsation, the common approach of treating pulsation as a small amplitude perturbation breaks down. So we need to use hydrodynamic pulsation models. And in this case, the feedback from pulsation on the structure is such that we have a nonlinear period of saturation. At a certain point, it doesn't matter how much the star expands, the period will settle to a sort of fixed value. So we recover the kind of behavior we expect from observation. So this is just to give you an idea of some complications we have in the business of modeling these stars. An interesting fresh result we had recently this year with my collaborator Giada Pastorelli is that if we try to study by hydrodynamic 1D pulsation model at which point stars start to pulsate on the giant branch, we find that this happens at the very transition between Ozarks and semi-regular variables. In other words, as a star evolves, it behaves as an Ozark as long as its oscillations are intrinsically stable, but keep being driven by the injection of the stochastic injection of acoustic energy from turbulent convection. This is called solar-like oscillation, so it's what happens in stars like the Sun and in early evolution red giants. And eventually, these stars become actually unstable to self-excited pulsation, much like what happens in Cepheids by an opacity-driven mechanism, and we call them semi-regulars or Myras. This is especially interesting because this transition is linked to other processes and phenomena. In particular, when we transition in a period luminosity diagram between Ozarks and semi-regular variables, blue to red means a step up in mass loss rate. It also, at this very transition, what happens is that these stars tend also to display additional variability in the longest period sequence that I briefly mentioned earlier. Turns out this other sequence is not due to pulsation, but to binarity. So the current accredited scenario is that as the star evolves, it turns from an Ozark to a semi-regular variables. Pulsation, self-excited pulsation acquires a coherent pattern able to increase the average density in the atmospheric profile, which fosters the production of dust. And then dust is accelerated outwards by radiation through a stellar wind, generating mass loss, enriching the circumstellar environment in dust. Now, if there is a substellar companion otherwise invisible, it can modulate the dust. And indeed, this is what Sushinsky and collaborators saw in 2021. If you look at the light curves in the optical and mid-infrared folded by these long periods, you're going to see a secondary minimum, which is probably a secondary eclipse. So the current idea is the substellar companion around the giant star collects, gathers gravitationally a cloud of dust that can eclipse or at least attenuate the light of the primary giant once per orbit. And this is the topic of the convergence project of which I am the PI at the University of Padova. We're trying to produce a simplified model of this phenomenon as it can be used to constrain mass loss rate and perhaps to characterize the population of substellar companions around red giant stars. Now, interestingly, last year, Goldberg and collaborators proposed a little variant of this process in which instead of gathering this kind of cloud of dust, the substellar companion actually digs a sort of a hole in the circumstellar dust environment, revealing the red giant once per orbit. And they did so using fresh radial velocity time series from the Gaia program. So it's an active field of research, very exciting. Now, a few words that will bring me to talk about WST. These stars, MIRAS, are promising distance and age indicators because, of course, they follow a pure luminous relation. This is in the case of the galaxy NGC 1559, which is a host of supernova type 1a, studied by Wang and collaborators 2020. These are promising because maybe, possibly, hopefully, they can be used to mitigate the Hubble tension. Also, MIRAS follow a period-age relation, so they are promising tools for dating stellar populations. Then again, MIRAS come in two flavors, oxygen-rich and carbon-rich, because of the convective mixing that can bring dredge up material from nucleosynthesis region to the surface, altering the molecular chemistry of the surface and resulting in drastically different photometric and spectroscopic properties. In brief, these applications are currently reserved to oxygen-rich MIRAS. So we need to be able to distinguish between these two chemical types. One way to do so is photometrically. An accurate combination of optical and near-infrared photometry can be used to produce this kind of diagnostic diagrams in which you see different groups. So this way you can distinguish between oxygen-rich on the left part of this right panel or carbon-rich. Problem is that not only this requires at least 4 different photometric bands in the optical and near-infrared, you also can only apply this to LMC-like metallicity, and there are sources that are, for instance, oxygen-rich but mimic as carbon-rich. So it's not always accurate and precise. So we move to spectroscopy, but we still need these for a large number of sources. Gaia provided us with low-resolution spectra. You can see here in the RP band. We can play a trick here. You see spectra, low-resolution spectra for oxygen-rich and carbon-rich source, and these dips are unresolved molecular bands. Turns out that near the peak emission, the molecular band is systematically narrower for oxygen-rich sources compared to carbon-rich sources. So we can exploit this to distinguish between the two. But even in this case, we have a number of complications, so it doesn't always work. So I asked myself, what can we do? What can we hope to do with WST? So I naively took the specification from the white paper and placed the WST footprint on the center of the Large Magellanic Cloud. And I looked at the sources from the Ogle 3 catalog that fill this field of view. So outcome is that if we focus on semi-regulars and MIRAS, that are probably the most promising one as distance and age indicators, we have around 3,000 semi-regulars in the multi-object spectrograph field of view, and around 500 MIRAS, mostly carbon-rich MIRAS. Now, my understanding, but please correct me if I'm wrong, is that with these kind of numbers, more or less, one could expect to use WST in the high-resolution mode. And this would be great to collect a lot of information simultaneously for a large number of sources. This is what people like me dream of for these stars, because we can do chemical classification with cross-correlation techniques. In principle, we can measure phase-dependent radial velocity and characterize the pulsation dynamically for the stars. And if you look at the distribution, my understanding is that with this kind of brightness distribution for the LMC down to 2021. In most cases, this kind of spectroscopy is expected to be doable. Now, I'll just briefly summarize an evolutionary aspect of these stars to present a few more applications that I have quickly thought about. So this is a schematic structure of a thermally pulsing asymptotic giant branch star. So a star that is quite about to end its evolution. Besides the dynamics in the outer envelope and atmosphere, illustrated in the left part of the diagram, we have intense processes in the interior. Of course, we have nuclear burning into shells. So we have CNO cycle hydrogen burning in an outer cell, triple alpha helium burning in the inner cell that produce nitrogen, carbon, and oxygen. And these are mixed, maybe mixed recurrently through the envelope and up to the surface once every time that the helium burning shell undergoes a helium shell flash, because it's intrinsically thermally unstable. This process also results, favors so-called slow neutron capture reactions that produce elements heavier than iron, like barium, lanthanum, and technetium. They all get mixed in the atmosphere, in surface atmosphere, and can be observed. Then, of course, this results through the combination of mixing and shock waves in the formation of dust grains in the atmosphere. They are very opaque. They absorb momentum from the radiation field of the star, are accelerated outwards, and result in mass loss and the enrichment of the interstellar medium. So it's crucial to understand the stars also for the purpose of studying the chemical evolution of galaxies. Now, my understanding is well within the expected capability of WST to reproduce this kind of study by Utintali and collaborators 2024. These three panels, vertical panels, show the spectral region associated with some lines of technetium, which is a radioactive S-process element that is direct evidence of both mixing and nucleosynthesis in the stars. Blue lines are stars that are technetium poor, red are technetium rich. So this is a way of distinguishing between different evolutionary states of these stars, but is powerful information also to constrain mixing, nuclear processes, and in general to understand the chemical evolution of stars and galaxies. Another kind of application that I expect can be possible in a large scale in terms of number of sources with WST, which is one of the flagship feature aspect of WST, in my understanding, is, for instance, to study atmosphere dynamics through this nice phenomenon of line doubling. So if you observe at different times, several lines over 2 years by this paper of Alvarez and collaborators, you'll see line doubling due to the fact that you are observing a different depth to the atmosphere of a star, and you see both the expanding shock front and the infalling delayed layers above the shock. So this is especially interesting because you can do actually atomography of the atmosphere and the star and study the dynamics, the mass loss, and so on. In general, and I'm going to close with this, being able to perform phase-dependent spectroscopy for large number of sources and for several epochs over a multi-year baseline, it would be very valuable for our studies of long-field variables for a number of reasons, but from the standpoint of a modeler, because this would provide us observational support to constrain our models of these stars that currently very often rely on hydrostatic atmosphere models, which are clearly inappropriate for such highly dynamic objects, and represent a crucial point for all the applications for these stars, from understanding evolution of the stars themselves, from their impact on the evolution of galaxy to their applications for distance and age estimates. So I hope I stayed within 20 minutes. Apologies if I ran a little bit through. And I hope this was interesting for you. Thank you very much.
Thank you, Michele, for your interesting talk. It's now the time for questions and discussion. I will start. I have one general question about the way in which do you think that the community can ensure that long period variables have the same attention to they deserve in competition with some popular pulsating stars like Cepheids and RLR? And instead, looking to the near future, what do you think that Gaia DR3, the Gaia DR4 and beyond can investigate that are out of reach now?
Okay, well, concerning your first question, it's, well, I often advertise the applications of LPVs as I did today, the impact they have in understanding stars and the universe. I don't think they're really, so to speak, competitors for CFITs and RLI because the underlying physics is very much the same. And actually, in my opinion, it would be very important to produce common routes theoretically for studying these objects because they can be used in a complementary fashion to constrain each other.
Coming distance and age indicators that like Cepheids, so it would be nice to.
Yeah, this is a very good example. I mean, they probe different kind of ranges. For instance, a number of LPVs, semi-regulars, are for instance, the near-infrared, they are comparably bright, if not sometimes brighter than Cepheids. And this is definitely the case for Miras. So they can probe further distances. But then again, they are more complex objects, so they have to rely in a way to calibration also assisted by Cepheids to perform as we would like. Now about Gaia, well, with year 4, we will have quite a massive release of information because all the information time series, low resolution, high resolution spectra, astrometric time series will all be delivered. I hope we will be able to build on the previous experience from the Data Processing and Analysis Consortium to understand, process, and analyze these data sets as part of the DPAC. I hope what we did will be useful to the community, but the greatest hope is that, as is usually the case, the community will overperform and find really new ways to cleverly exploit this kind of data. So I'm eager to see what's going to happen in a couple of years or such.
Okay, thank you. You have a question by Nami Molavi.
Hi, Michele. Very nice presentation. Can you say a word on what you think should be or could be next steps in order to refine the distance estimation potential of these LPVs?
Thank you for this question, Nami. So my personal opinion is that currently the protagonists of this kind of application among LPVs are the Miras, but there is untapped potential from semi-regular variables that are, as I mentioned, often quite similar to Miras in variability pattern in terms of also of regularity. They are thought to be the progenitors of Miras and are often more numerous than Miras. So statistically speaking, this represents value. The issue is that we have an arbitrary, not well physically defined distinction between these two types. So I think there should be an effort in characterizing this kind of transition, in particular because there is evidence that, let me just go back a little bit. So I mentioned that there is this kind of distinction based on amplitude between semi-regulars Miras. But the amplitude, the photometric amplitude of these stars seems to depend on the metallicity, because the change in light is associated with the formation of molecules at the expansion and cooling phase. So it's easier to form molecules if you have more abundant metals in the surface and atmosphere, meaning that you have a systematic effects in the amplitudes of the stars, meaning that there could be a selection bias when you just pick Miras instead of semi-regulars for application like distance and age estimates. So there should be a physically informed interpretation and classification of the stars, in my opinion, to attain, to fully exploit their potential for distance and age estimates.
Maybe a related point or question is about the scatter of these period luminosity relations. Do you think is this totally intrinsic, and which parameters, if any, could play a role in this scatter? And if there is any parameter, would any observations be able to
Yeah, I see your point. There is definitely some kind of degeneracy there. It's a common approach is using period color luminosity relations, but amplitude itself, I believe, is a parameter that can be used to break this kind of degeneracy and reduce the intrinsic scatter of the relation if properly calibrated. Once again, there should be some information about environment metallicity, but the advantage of using this kind of information, for instance, amplitude instead of color, if properly understood and calibrated, is that amplitude is much less affected, for instance, by extinction compared to colors that may be affected by reddening. So it would be great if we could find a way of characterizing these relations with, so to speak, purely variability related parameters.
Yeah, I guess the spectroscopic capabilities of WST combined with time domain studies might provide some insights there.
And it could definitely help both to characterize the chemistry, molecular chemistry, hopefully, although it's cumbersome task, but also providing radial velocities, which can be used to better understand the variability, amplitude, and the atmospheric structure of the stars, I guess.
Yeah, thank you, Michele.
Thank you, Nami.
Please, Anupam, go ahead.
Very nice talk. At some point, you discussed about the problems of modeling large amplitude pulsators. I was wondering, in your hydrodynamical models, what is the mechanism behind pulsations? Is it similar to kappa gamma mechanism for classical pulsators, or is there the main component or contribution comes from dynamics of their atmospheres, which might levitate materials, causing these oscillations?
So the strong driving region is usually associated with regions of partial ionization of hydrogen and helium. So this indicates that the driving mechanism is at least partially imputable to a kappa gamma-like mechanism. It's actually quite difficult to find conclusive results about this, because it turns out that convective luminosity, convective energy flux also plays an important role, it appears. The problem is, of course, that convection is treated in 1D models by some time-dependent flavor of the mixing length theory. So this kind of parameterized approach, let's say I would be careful in drawing specific conclusions about role of convection in driving this the position in the stars, but there is definitely some. What's encouraging is that 3D hydrodynamic models performed by people in the Uppsala group, Bernd Freitag, Arif Ahmad, Susanne Hoffner, they tend to be in agreement with the period predictions from 1D hydrodynamic models. So this means that in a crude fashion, we are getting the results. But there is a lot of interesting work going on to characterize the, as I mentioned, the 3D deviations from this. So summarize the answer, I would say the primary effect is some sort of opacity-like organo mechanism with some role played by convection that hopefully is going to be constrained better by modern 3D hydrodynamic models.
Okay. So just to add, so are you also able to produce with these hydrodynamical models light curve variations, not just
light curves?
luminosity? Are you also able to generate light curves of these long period variables and not just the period luminosity relation sequences?
Yeah, that's a tough point. We are not really able to construct accurate light curves. We more or less get there, but the primary problem here is not really associated with the pulsation dynamics. The pulsation dynamics happens in a subphotospheric region and is quite accurately captured by these models. But the current models we are using, the code we're using for computational efficiency reasons, does not incorporate an accurate treatment of radiative transfer in the atmosphere, which should include the effects of the hydrodynamic effects of molecule formation, dust formation, and so on. So that's a key ingredient that must be plugged into these models to actually simulate high accuracy light curves for these stars. So for the time being, we are sticking to the periods. We are working to improve on the radiative transfer in the atmosphere. And I'd like to say that with the results we published with Gaia in the focus product release and are coming with year 4, we're also using now radial velocities to impose additional constraints on pulsation models. So this is going to be an exciting time when year 3 comes out for this reason as well.
Thanks.
Thank you.
I have another question. First of all, regarding the problem of convection, we have the same problem also for modeling classical Cepheids and RLR. But I was thinking about the use of age indicators for LPV. Which kind of evolutionary model do you use? It's better to use for using them as age indicators.
I'm sorry, I'm not sure I understand the question.
Using them as age indicators, no?
Yeah, they can be.
Use evolutionary models for sure, I think, no? You have to.
Yes, we have worked actually with NAMI on the period age relation of these stars. To do so, well, first of all, it turned out that the hydrodynamic models are absolutely necessary to predict the period age relation on model-based grounds. So I'm not showing it here, just to give you an idea. We combined evolutionary models from Parsec database with hydrodynamic pulsation models to reproduce the period age relation. We found it to be in agreement with long period variables located in clusters of known age. But it's worth mentioning that probably I mean, this is in my opinion, but it's been supported by some studies, also by standards and collaborators. It seems that there's not really a universal period-age relation. It also depends on stellar population properties. So this is something that I hope people will look into in the future.
Okay, thank you, Michele.
Thank you.
Other questions? Okay, I think we can conclude the session here. Thank you, Michele, again for sharing your work with us.
Thank you very much.
For contributing to the discussion. We look forward to seeing you at next talk that will be Dr. Anupam Bardaj on June 19. Have a great day, everyone. See you next time.
Yes, and if we have to remind you, then it's not going to be another Tuesday, it's going to be another Thursday. So please stay tuned. And yeah, like we're going to send you also the reminder emails, etc. So yeah,
Okay.
thank you, everyone. See
Thank
you.
you very much.
Bye.
Goodbye.